Swayam Prabha. Digital India. Educated India.
We finished our last lecture with the contact ratio for a pair of involute gears. What is the expression of the contact ratio? Today we start our discussion with the expression of the contact ratio for a rack and pinion drive. So, contact ratio, we use the symbol MC for a rack and pinion. Let us say this is the pitch circle of the pinion. For the rack, as we know, the pitch circle radius is infinity, that is, the pitch circle gets converted into a straight line. As in the case of a pair of gears, two pitch circles was touching each other. Here again, the pitch line of the rack is in as a tangent to the pitch circle of the pinion. So, this is what we call pitch line of the rack. And this is the pitch circle of the pinion. If we draw the base circle of the pinion, this is the base circle. This point of contact between the pitch circle and the pitch line is the pitch point, which we denoted by P. From this pitch point, if I draw a tangent to the base circle, from this pitch point, let me draw a tangent to the base circle. This line represents the line of action. Let this point of tangency be, I denote by A. This is the center of the pinion. Then this angle is the operating pressure angle phi, which is same as this operating pressure angle phi. The point of contact between the teeth of the pinion and the rack always moves along this line of action. Let me talk of a particular tooth on this pinion which is just beginning the engagement. That means the contact with that particular tooth is just starting at this configuration. Let this be the tooth which is coming in contact with the tooth of the pinion at this instant. Now, where does the contact start? Contact obviously starts at the addendum line of the rack, that is the highest point of the rack tooth. So, the rack tooth, if I draw, this is the addendum line of the rack. So the rack tooth is perpendicular to this line of action. So let this be the rack tooth. The contact starts at this point between the pinion tooth and the rack tooth on the line of contact. This is the addendum line of the rack. If I complete the rack tooth, it will look something like this. This is the rack. At this beginning of the contact, this point let me call E. Now this gear, this pinion rotates in the clockwise direction. This pinion rotates in the clockwise direction, drives the rack to the left. Now when does this contact between this pair of teeth is lost? It is lost when the contact comes at the addendum circle of this pinion. Let this be the addendum circle of this pinion tooth. If I complete the pinion tooth, it looks like this. When this addendum circle intersects this line of action, let's say this point I call S. This tooth has rotated and let's say this is the addendum circle. This point is F. Now how much is the movement of this tooth measured along the base circle? Let me call this point S, this point on the base circle, and the tooth has rotated and the movement along the base circle is from S to T. This is due to the rotation of the gear. This point S of this tooth has moved up to this point T. Now to ensure that the teeth remain in contact, the next tooth, that is the adjacent tooth on this gear, this point must get into beyond this point. This point must move beyond S such that this tooth comes in contact with the next tooth. And this distance measured from this point to this point, let me mark it, the distance between these 2 points on adjacent tooth along the base circle, that is what we denoted as base pitch or PB. The distance between 2 adjacent teeth along the base circle, that means from this point to this point, that is what we call PB. An expression for PB we have used last time, which is 2 pi RB divided by N, where RB is this base circle radius, OA, this is RB, and N is the number of teeth on the pinion, RB is the base circle radius of the pinion. Now, contact ratio MC was defined as the movement of one tooth along the base circle, which is ST, divided by the base pitch. And as we said, this must be more than 1, so that continuous transmission of motion from between these two, rack and pinion, is ensured. Now to get the expression of this MC, let us see the contact started at E and finished at F, and these are involute profiles. So AS is nothing but AE. AE is the string length which was wound onto this base circle, and by unwinding I have generated this involute profile. Because it is an involute profile, the distance AE is same as the distance measured along the arc of the base circle AS. So, AE is same as AS. Similarly, this is also an involute from the same base circle, is the same tooth. So, AT, this measured along the base circle, will be AF, that is the length of the string, which has been unwound from this base circle. So, AT is AF. Length of the string AF is the length of the circular arc from A to T. So, if I subtract AF minus AE, I get EF, and if I subtract AS from AT, I get ST. So, ST is same as EF. So, that I can write again, contact ratio is nothing but EF by PB. EF I can write as EF this is EF, this point is E, this point is F. So, I add AE. And I also subtract AE so that way I get, okay, let me not write this way, let me write it a little differently. I write it as EP, EF I write EP plus PF. EP is this distance, PF is this distance divided by PB. Now, I add PF AE plus EP. EP I have written EP, I add AE to PF, and I again add EP and subtract AE plus EP, that is AP. EP I have written here, PF I have written here, AE plus EP I have added, so I have subtracted AE plus EP, which is nothing but AP. AE plus EP, which is nothing but AP, divided by P. So, finally, I get MC, the expression of MC, contact ratio, is EP. What is EP? EP is this height, which I can see if this angle is phi and this vertical height is addendum of the rack, which I denote by AR. AR is the addendum of the rack. So, this EP is nothing but AR by sin phi, where phi is the operating pressure angle. This is EP, and PF plus EP plus AE is nothing but AF. Whole thing is divided by PB. This is AF and minus AP. A is this contact point between the tangent from the pitch point to the base circle. So, this angle is 90 degree. This is radius, this is tangent, so this angle is 90 degree. And O1P is nothing but the outer radius of the pinion. This is the outer circle, this addendum circle. So, O1 to F is nothing but the outer circle of the outer radius of the pinion. So, AF is square root of outer radius squared minus RB1 squared. So, this I get AR by sin phi plus this is RO1 squared, that is the outer radius of the addendum circle radius. This is what I call RO, R outer 1 minus RB1 squared minus AP. AP is nothing but, this is phi and this is RB1. So, AP is RB1 tan phi. Tan phi is AP by RB1. So, AP is RB tan phi minus, let me call it RB1. I am writing RB1 here. RB1 tan phi divided by PB, for which I already wrote the expression. So, finally, we have got the expression for the contact ratio for a rack and pinion drive involving the addendum of the rack, operating pressure angle, outer radius of the pinion, base circle radius of the pinion, and the base pitch, which is PB is nothing but 2 pi RB divided by N, RB1 N1. RB1 is the base circle radius, N1 is the number of teeth of the pinion. So, this completes our discussion on the contact ratio for a rack and pinion drive. The methodology is just similar to what we used for a pair of involute gear teeth profile. Now that we have finished discussion on contact ratio, let us start with a very important parameter for gear tooth geometry, that is known as interference and undercutting. First, let me explain what do you mean by interference and what is undercutting. If you remember, from the very definition of involute profile, it is obvious that the involute does not exist inside the base circle. It is from unwinding from this base circle outward, we created the involute profile. Let us say we start from this point A, it starts radially, and as the string unwinds, we generate this involute profile. So, the involute profile exists only outside the base circle, does not exist inside the base circle. Suppose we use very few number of teeth on a gear and the teeth size is very big, then it may so happen that the addendum circle of the mating gear gets into the base circle of the other gear. But if the mating profile, which is another involute from another base circle, gets into the inside the base circle, as we see, there is no involute of this gear, say this is gear number 1 and this is 2. The gear number 1 does not have any involute inside this base circle, whereas the involute of the other mating gear is getting into the base circle. So, there is no conjugate profile. So, what one can do? One can extend this involute of gear 1 maybe radially. Even then there is interference. As we see, this tooth will interfere with this tooth because this tooth wants to occupy this position, whereas this tooth is lying there. This is called interference. One solution to this interference is to remove some portion of gear 1. We do not have the involute profile for gear 1 anyway. So, let me cut this portion from gear 1. Then as we see, this gear tooth is not interfering with gear 1. The tooth of gear 2 is having a space inside gear 1, though there is no conjugate profile to maintain contact. However, the conjugate action may be taken care of by the other pair of teeth in engagement. So the continuous motion is transmitted maintaining the constant angular velocity ratio, but this tooth is not transmitting any power because this is getting into this portion. And this is what is called undercutting. We have avoided the interference by undercutting the tooth of gear 1 inside the base circle. But this is not a very satisfactory solution because this undercutting weakens the tooth of gear 1. Undercutting which weakens the undercut tooth. And it is here at the root of the tooth where failure takes place. So if we have weakened the tooth near its root, that is not a very desirable solution. Only if it is a must, then only we should undercut the tooth. Next we shall discuss how to ensure that there is no interference, how to avoid interference by ensuring some minimum number of teeth on a gear. We cannot have number of teeth on a gear less than a minimum number to avoid interference. That will be our next topic of discussion. As we have just now shown the possibility of interference between a pair of gear teeth because involute does not exist inside the base circle, one not so satisfactory solution was to undercut the tooth. But a better solution is to have a minimum number of teeth on a gear to avoid interference. We have already seen how does the interference take place first of all, because the addendum circle gets into the base circle. So now we talk of a minimum number of teeth to avoid interference to transmit a particular angular velocity ratio. To transmit angular velocity ratio say we call it lambda, which is defined as omega 2 by omega 1, which is less than equal to 1. That means omega 1 is more than omega 2. When we transmit continuous rotation from one shaft to another at a constant angular velocity ratio, let us forget about the sign for the time being. I define the angular velocity ratio only by the positive number, and I define it in such a way that it is less than equal to 1. That means the higher speed is at the denominator. For example, suppose lambda is 8 upon 9. Now to transmit a constant angular velocity to 8 by 9, I can have 16 and 18 teeth or 24 and 27 teeth or 32 and 36 teeth. The question is, what must be the minimum number of teeth to transmit angular velocity to 8 by 9? Can I use 8 and 9 teeth to transmit constant angular velocity to 8 by 9? That is the question we are trying to answer. What is the minimum number of teeth such that interference is avoided while transmitting a particular angular velocity ratio which is given to us, the value of lambda. Towards this end, let me first draw the two pitch circles. Suppose these are the two pitch circles. omega 1 is the higher speed. So, this is gear 1 which rotates at a faster speed, and this is gear 2 which is rotating at a slower speed. Suppose this gear is rotating this way and this gear is rotating this way. These are the pitch circles. Now, let me draw the two base circles. These are the two base circles. This point is O1, this point is O2. This is the pitch point which we call P, and if I draw the common tangent to these two base circles, that is the line of action A, B. Now, as is very clear, because this is a smaller gear, AP is smaller than BP. This is a larger gear which is rotating at a slower speed. So, lambda is N1 by N2, where N1 is the number of teeth on this gear, N2 is the number of teeth on this gear, which is also same as O1P divided by O2P, and which is same as now the question is that addendum circle of either gear should not get into the base circle of the other gear, and as we know, the contact point is restricted to move on this line of action, that is line AB. So, which addendum circle will first get into the base circle? Addendum circles are of same size, both the gear's teeth are of same size, they have the same addendum. So, it is obvious that the bigger gear addendum will first get into the base circle. If this is the addendum circle, if this touches A, the addendum circle of this gear, which has exactly same addendum, will still pass through the below the point B. It will not get into the base circle. The point of contact always lies on this line, so I am only interested in seeing whether the addendum circle of this line intersecting AB beyond A or beyond B. So, interference obviously occurs first with the pinion when the addendum circle of the gear just passes through the point A, because even at that time the addendum circle of the pinion does not pass through the B, it is still to interfere with this gear. So, first point to note, interference occurs first at the pinion, that is the smaller gear. And we are considering as if the interference has just started. From this diagram, we should be able to find out what is the minimum number of teeth, that is N1, to avoid interference. That is the task. And this common tangent to the pitch circles, this is the point P, and this angle is the operating pressure angle phi. Now, this distance O2A, which is nothing but the circle of the radius of the addendum circle of gear 2. So, let me first write an expression for this O2A. We consider the triangle O2PA. This point is P. Let me write it here again. O2PA. Let us consider this triangle. So, O2A I can write O2A squared is O2P squared plus AP squared minus, just using the triangle law, twice O2P into AP into cosine of the angle between O2P and AP, which is pi by 2 plus phi. We consider the triangle O2AP. O2A squared is O2P squared plus AP squared minus twice O2P into AP into cosine of the angle between them, which is pi by 2 plus phi. So this I write O2P squared plus AP squared minus twice cosine pi by 2 plus phi is minus sin phi. So I get plus 2 O2P into AP into sin phi. So, and what is AP? This angle, if you remember, you have used it number of times, this angle is also phi. So what is AP? That is O1P sin phi. So this I can write O2P squared plus O1P squared sin squared phi plus twice O2P, and for AP I write O1P into sin phi and another sin phi, so I get sin squared phi. So now if I take O2P common from this expression and take the square root, I get O2A is O2P into, from here I get 1, here I get O1P squared divided by O2P squared, and if you remember lambda, this was equal to O1P by O2P. The speed ratio is nothing but the pitch circle radius ratio. So lambda is that. So if I take O2P squared, I get here lambda squared sin squared phi, and from here I get 1 lambda. So 2 lambda sin squared phi to the power half. I have taken O2P common from this expression. So I get 1P by O2P, which gives me this lambda. Here I get 1P squared minus O2P squared, which I get lambda squared. And then I have taken the square root. Now O2A minus O2P. O2A is the addendum radius, O2P is the pitch circle radius. So the difference of this is nothing but M. No, sorry, addendum. O2A, O2P, O2A minus O2P, that is the addendum O2A minus O2P. So if I use this expression of O2A, I get this as O2P one plus lambda into lambda plus 2 sin squared phi to the power half minus 1. This is the expression for the addendum. Now, addendum is always expressed as a fraction of the module. Addendum is always expressed as a some fraction f of the module. If you remember, for the British standard for 20-degree pressure angle, we said f is normally 1, but I keep it as f, which is of the order of 1. So A, which is f into m, is O2P into this expression, which is 1 plus lambda into lambda plus 2 sin squared phi to the power half minus 1. And if you remember what was the module? Module was 2 into Rp divided by number of tooth. Module by definition is pitch circle diameter by the number of teeth. Number of teeth of the second gear, pitch circle diameter of the second gear. So, this O2P I can write as Mn2 by 2. If I write Mn2 by 2, cancels, so I get N2 is O2P, I am writing Mn2 by 2. So, 2F divided by this expression. We have considered the situation where interference just started with the pinion, and we would get this expression for N2, which means if I multiply by N1 by N2, which is nothing but lambda. So, N1 minimum tooth on the pinion, we get 2F lambda divided by this expression. The denominator remains the same. Two F lambda divided by 1 plus lambda into lambda plus 2 sine squared phi, this whole thing to the power half minus 1. So, this is the minimum number of teeth required to avoid interference while transmitting an angular velocity ratio lambda, and lambda as we have defined is always less than 1. So, this is how we get the minimum number of teeth to just avoid interference. N1 at least should be this much. If N1 is more, then there will be teeth will be smaller, so there will be no problem. This is just when the interference starts. So, N1 should be more than this N1 minimum. Just now we derived the expression for the minimum number of teeth that must be on a pinion so that interference is avoided while transmitting a constant angular velocity ratio lambda. Number of teeth on a pinion must be greater than N1 minimum, where N1 minimum was given by 2F lambda divided by 1 plus lambda into lambda plus 2 sine squared phi to the power half minus 1, where lambda by definition is between 0 and 1. We always define lambda as less than 1, that is the slower angular velocity divided by the faster angular velocity, and phi is the operating pressure angle. What is F? F is addendum is expressed as a constant fraction of the module. It is this constant fraction is F. F is normally 1 unless otherwise stated. From here, let me try to derive the expression for the minimum number of teeth that must be there on the pinion while it is in contact with a rack, for rack and pinion. If it is rack and pinion, then what must be the minimum number of teeth on the pinion to avoid interference? For rack and pinion, as we see, lambda is 0, because the angular velocity of the rack is 0. Rack has only translational velocity. So, lambda is 0. Omega 2 by omega 1 is 0. Now, if I put lambda equal to 0 here, then I get 0 and this is 0, so on, it is 0 by 0. For this N1 minimum from this expression is turning out to be of the form 0 by 0. But that is nothing problematic. As we know, we can always take the limit. Let us take the limit of this as lambda tends to 0. So, for rack and minimum, I can get N1 minimum by taking the limit of this expression as lambda tends to 0. Because it is of the 0 by 0 form, I can use L'Hopital's rule. That means differentiate the numerator with respect to lambda, denominator with respect to lambda, then put lambda equal to 0 and see what is the limiting value. So, that way if I take derivative of this with respect to lambda, on the numerator I am getting 2f, and the denominator if I differentiate with respect to lambda, I get half, then this goes at the top 1 plus lambda into lambda plus 2 sine squared phi to the power half, and here I am getting lambda squared is 2 lambda plus 2. If I differentiate derivative of the numerator and derivative of the denominator, this is what I get, half into this to the power minus half, then while differentiating this I am getting with respect to lambda, if we are getting sine squared phi. Sine squared phi, lambda squared gives me 2 lambda and 2 lambda gives me 2. And now I put lambda equal to 0. If I put lambda equal to 0, this goes to 0, so I get 2f, and here if I put lambda equal to 0, then 2 cancels, we get sine squared phi. So, this is the minimum number of teeth on the pinion which engages with a rack and without interference. There will be no interference. This expression, of course, we could have got geometrically very simply by drawing the rack just undergoing interference with the pinion. That is what we are going to do next. Just now we derived the minimum number of teeth on a pinion that is required to avoid interference with a rack. But that we did analytically from the expression that we derived earlier for a pair of involute gears, a gear and a pinion. Let me now get the same expression of the minimum number of teeth geometrically. So, N1 minimum on the pinion for a rack and pinion to avoid interference. Towards this end, let me say this is the pitch circle of the pinion, and this is the pitch line of the rack. This is the base circle of the pinion. If I draw from this pitch point P, if I draw a tangent to the base circle, this angle is phi. This is O1, this is the. Now, if the addendum line passes through the point A, if this is the addendum line of the pinion of the rack, that is, the rack tooth looks something like this. If the addendum line intersects this base circle just at A, that is when the interference starts, and you can use this diagram for getting the minimum number of teeth on the pinion. This is the rack of the addendum AR, which we write as F into M, and this angle is the operating pressure angle phi. So, AP is AR sin phi. Just when the interference starts, AP is AR divided by sin phi, and AP is also O1P sin phi. This is O1P sin phi. This angle is 90 degree. This is the base circle and radius, and this is the tangent. This angle is phi. So, pitch circle radius is O1P and AP is O1P sin phi, which tells me AR, which is F into M, is O1P sin squared phi. And what was M? M, if you remember, is nothing but 2 into O1P by N1. Pitch circle diameter by the number of teeth, that is the definition of the module. So, this if I place that, I get N1 M, I am writing twice O1P by N1, O1P cancels, N1 is 2F by sin squared phi. This is the same expression that we got earlier by taking the limiting value from the expression of N1 minimum for a pair of involute gears. Next, we shall solve an example to show the application of this expression that we got for N1 minimum. How do we determine the minimum number of teeth or the number of teeth that must be used to transmit a particular given angular velocity ratio lambda? Let me now solve an example for a pair of involute gears to transmit an angular velocity ratio lambda as 8 by 9. Lambda is given to be 8 by 9, and the operating pressure angle phi, just as an example, let me take 14.5 degree, which means sin phi will be 0.25. If you remember, the expression for N1 minimum was given as 2f lambda divided by 1 plus lambda into lambda plus 2 sin squared phi square root minus 1. Now, f, the most usual value is 1, so let me say f is taken to be 1. If I put f equal to 1, lambda equal to 8 by 9 and sin phi equal to 0.25, N1 minimum from this expression turns out to be 22.94. But number of teeth cannot be 22.94, it has to be an integer. So, N1 minimum looks like it should be 23. But if N1 is 23 and to transmit an 8 by 9 angular velocity ratio, N2 will turn out to be a non-integer, which means this will imply N1 has to be a multiple of 8 such that N2 can be a multiple of 9 and they will be both integers. So, N1 minimum is actually 24 and corresponding N2 is 27. So, if I use 24 and 27 teeth, I can maintain a constant angular velocity to 8 by 9 and without interference. So, this is what we mean by minimum number of teeth to avoid interference.